That look normal to you? This is like a meal, a full meal. Well, not really, but like you know.
This is cool to me.
Didn't I just hand you your?
Why? It only increases my.
Well, here, no, here it is.
You're good. I'm trying to convince myself that it's not worth it to do it.
Okay.
Every time I do it, it's not.
Just
So
yeah,
you
erase it
went-
after time.
Went well, a lot of scores in the 90s, some in the 80s, a couple lower, but generally quite good understanding of material. And so for the exam two, it's kind of one outstanding issue, but then not concerned with anybody here. And so post the solutions on Wednesday. So those will be coming, so you can compare to look at those things, right? In general, things went quite well. Some, I guess, the one issue. So on the normal probability problem, number 4, not everybody saw that it was just a normal calculation. And instead try to do something with binomial or change it into a t-test procedures, and so some partial credit was given if it was kind of reasonable there. On the number 5 was this two-way table, and one question: what's the expected number of full-size tires among cars carrying only one? Well, if you know it's only carrying one, then it's only about that one column. So it was necessary to compute conditional probabilities. Or what's the probability that you're at 4, 5, or 6 tires in that column? So kind of standardize that and then compute an expected value. So
Can you show us? So I see.
yeah, so in this one there was this two-way this table that had 4, 5, or 6, or 0, 1, and 2, and these were the large tires, and these were the small spares. And that last question said, what's the chance that you were, what's the expected number, given that you had one small spare there, that you were one of these ones here, and it was 64% overall. The probability of these three counts, 63% and 1%. And so the probability that you had 4, this is X, and this is Y, just to use some symbols, given that it's 1, well, it's the probability of both of those things, so that the 60% over out of the 64%, and the probability that you're 5, given that you're 1, there was 3% out of the 64 were there, and the probability that you were 6, given that y equals 1, there's 1% out of the 64. And so then the expected value of that was, you would take this probability times 4, and this probability times 5, and this probability times 6, and then add up those numbers. So you compute the probability, so they add up to 1 just within that column, and then take an expected value. But solutions will be posted on Wednesday, and you can look at some of the other ones. But in general, people did quite well in terms of points still coming in the class. A few more homeworks, project. The project was assigned last week and is due at the end of the class. So be thinking about that in the final. So many of you are in a very good position, having done the homework and the exams. They had a good finish here, and very good. Be able to get a good grade out of it. So the solutions will be posted Wednesday. There's a homework due Friday on analysis of variance. And I'll be gone on Friday as planned. And so you could submit the homework. There'll be a folder outside of my office, and you can just put it in there. I think today we'll have covered most material for that homework. And then on Wednesday, go on and look at other forms of analysis of variance, some slight enhancements. You'd have a lot of the material, so if you ask about office hours, in office hours or in class on Wednesday, if you have any questions. I have to leave kind of after my classes today to go to my daughter's school, so I won't be around for office hours this afternoon, but I should have my regular office hours the other times. So we looked last time some at analysis of variance, and the key ideas in this is we have some measurements. The book uses X's, and so there are groups in the data. These could be experimental groups. They could be we just sample the world and classify into different groups. And then there are individuals. And it could go up to n sub I. The book generally keeps this as a constant number here, but you don't necessarily have to do that. And the business of analysis of variance is decomposing the observation, this xij, into the difference between that and the overall average into one that has an average for group I, and the difference of that group versus the overall average. And if we squared that and summed everything up over all the cases, we got a decomposition of sum of squares of things. And so if we decompose this to get sum of squares total, we'll call SST. This one is the square is an error, sum of squares, and this one, when it's squared and added up all the cases, became a sum of squares treatment. And what we want to use this decomposition in is to judge, is there really a difference among these groups? Is the average of these groups substantially different? We know that there's some variability of measurement, so they won't be exactly, all the averages in the groups won't be the same exactly no matter what. And is it more variability than we would expect by just random chance? And so today we're going to look at a numerical example that goes through this and look at it on the computer, and then take up what do you do after you do that initial testing. So here's a handout that you have. Bigger. Right. And so this is an effect of a drug on memory. Right. Scopolamine induces sleep in patients. What impact does it have on memory? So to study this, they had 28 subjects, recruited volunteer, and they gave a pair of words, list of word pairs, like robber and jail, or the things that would be clouds and rain, or something like that, right? And studied it looked at the words before they went into surgery and were given the, or not, well, this was just studying the impact of this drug, so they weren't given actually having any type of surgery, but they had either that drug or they had a placebo, so they were taking something, right? If people think that they're taking something that could affect their memory, maybe it will affect their memory, right? They won't try, or they'll get kind of a psychological block or something to stop that, or no drug. And they asked how many after a period of time, they asked them which of the words can they remember, and they get a score. It's a fairly small study. So there's coplamine, a placebo, or no drug. And so in this case, the treatments define these groups. It's pretty clear that some get one, the scope of active drug versus a placebo, which could be made to look like that or taste like the other one, or somehow indicate, make it seem like it's the same experience, but not the active drug in it, versus no drug. So there's 3 groups. So in this case, our number I is 3. The response is going to be these number of words out of 12. Were there 12 words in all? Yes, so 12 word pairs, so the highest scores are 12. They can remember them all. Randomization gets used in this study, so the subjects come in, they get randomized to one group versus the other. In comparing these groups, it's very natural to compute the sample means. So if you do that in this group, the 3 averages, 6.17, 9.37, 10.65. Right, so this is scoplamine, and then the 2 that don't have that in there. Right? And so you would calculate those averages, and it kind of looks like there's a difference. Right? One looks different, a little bit lower. Right? It is statistically significant. So a few ways to go about that. These are the components of the sum of squares. The difference of the values minus their averages by group is squared, added over all the subjects in there. Right? It's also related to the standard deviation because that's the numerator of S1 squared. These are the sum of the squared deviations within groups. You add those all up, and that's the sum of squared error out of that. The overall average, what the book puts these extra 2 dots there, right? Meaning adding over the i's, adding over the j's, adding over both dimensions, both indexes, turns out is just a weighted average of all those numbers. The numerator in here, well, n1 times the average of the first one is the sum of the x1 j's. N2 times the sum of the average there is the sum of the ones in the second group, and this one then is also the sum of the individuals in the third group, and then this is over the entire sample size of these 2 things. So that's the average. Right? The sum of squares treatments would be the average of from each group minus its mean times how many people are in each of those. Right? So you calculate those, analysis of variance, then puts that into a table, right, to summarize the sources of variability. We're going to need the sum of squares treatment, sum of squares error, and be 2 components of it. And so on the next page, you have this. Fix this up, break that apart, and then I have to rotate it from over here, I think. Right. Reviewing this, rotate to counterclockwise. We make this little ANOVA table. We're looking at the impact of treatments or groups versus the error. We have our 2 sums of squares. They add up to 156. There are degrees of freedom associated with both of those lines. Treatments is the number of groups minus 1. Right? Kind of where this comes from is you have the K here is our book calls this I, so sorry, this has been adjusted for our book's notation. Different books will use different indices for all sorts of things. But there's 2 degrees of freedom here. There are 28 subjects in all, so -1 is 27, and those add up. There's 28 subjects, but once you're looking at the groups, there's 3 averages, so 28 minus that. Can't quite get this to go away. The mean squares, or the sum of squares divided by degrees of freedom, just like in a sample variance, you get the sum of squared deviations divided by an adjustment for the sample size. And we calculate this F statistic as a ratio of the mean squares for treatment versus mean square error. We get a value of 27. And we're going to compare that to an F distribution. So under the hypotheses of this, the null hypothesis and analysis of variance would be that the 3 groups all have the same mean in this case, and an alternative is that at least one is different. You could have all 3 being different, that would be fine. Or you could have 2 being the same and another one different. And it would qualify as this alternative. The underlying analysis of variance is a certain probability model that says the xij's are normally distributed with a mean for the group. And some variance. The null hypothesis says that they're all the values are kind of centered at one kind of common mean here. The alternative says they're normally distributed, but you could have different means of somehow, and they're separated. And I guess for our picture for this application, really the 2 upper ones are kind of similar, but the lower one is a little bit lower. So this one is more like maybe that's what the real underlying data model would look like. People's memory and their word recall goes down when they're on this drug. But under the null hypothesis, this F, so statistic, the F statistic, which is the mean square for treatment over the mean square for error, has an F distribution with the numerator as F is the ratio of 2 things, so there's a numerator denominator, and there's a certain degrees of freedom associated with both. This is associated with treatment, and this one is associated with error. And this F distribution is positive and skewed out like that. And so if our statistic, if we have a big mean square treatment, meaning a big difference in the means, we're going to be out here. So out in this area, we reject the null hypothesis. Out there. And so we generally look up at the 0.05 tail up there to decide whether we reject. And in this document here, we had 2 degrees of freedom for treatments. We got 25 for the error. And the tail areas for this distribution, 2.5 cuts off the upper 10%, 3.39 cuts off the upper 5%, and we're at 27. We're way out there, right? So the p-value definitely is less than that 0.01. And because of that, we reject the null included there. It really does look like there's a difference in memory recall. So let's see how that goes in R. So was this, yeah, so there's a code handout there has some of these commands. So if you have this small data set, it's not hard to enter it that small data set into there. Right? These are the numbers, and I call it just SC. It's an object that holds the scopolamine values. This one holds the placebo values. This one holds the no drug values. So if I just run these things, it just creates an SC. SC is just those values. PL is those values, and HO is those. NO, sorry, are the values. Right? That should match up to what's there. I usually enter those things and then look at them, double check them. If I have any summary information, I like to double check that my summary information matches up, that I have the right number of observations, so it's a little bit of checking. I write it like this for a handout. If I was just typing it myself, I'd probably just type the mean of one of these values to get an average. But on the handout, I can put all three together, and it will give me the means of all three groups. Of, the semicolon that executes all the different three commands. And we can calculate the standard deviations we want. Length will tell me how many observations are in each of those, the 12 in the first group, and then 8 in the other two. Right? I'm going to create an object that holds the data and then use the analysis variance command. So we're going to need something that tells it what the commands are. This repeating thing here repeats some values, right? And so if I just do that part of it, it's going to repeat SC 12 times, and then the PL 8 times, and NO 8 times. So it's going to copy that and just create a long 28 length vector that has these different designations in there, right? Those are my symbols. You could do it with numbers 1, 2, 3, right? In some commands in R, you have to be careful with if you put numbers in there 1, 2, 3, because it might think it is the numbers 1, 2, 3, and try to say there's a linear relationship and things like that. The letters do that. You wouldn't have to necessarily use this factor command. The factor means that in all my plots and things, it will keep it in the order SC, PL, NO, right? I'm telling it to keep it that way. The default in R would be make it alphabetical. So it would actually reverse it. It would go no drug, placebo, SC in all my graphs. But if I want it the other way, I can make it a factor and make it go that other way. Make it this factor, call it group. Now group just has these 28 values, and it tells me it has these levels. That's one kind of side effect of it. If you do a table of that, it says it has 12 in SC, 8 in PL, and 8 in NO. And I put these things, the words, and the word counts, and then the group designations together in something called a data frame. Kind of like a matrix, but it has a little more flexible referencing. And this is about memory, so I'm just going to call my data frame of results MEM, kind of abbreviation for memory. So words is my first column. It's going to combine together these three. See this concatenation here of putting these three things together. It's going to be my 28 numbers all in a row. The group, like we talked about, is 28 numerical lists. If I put all that together, and then I just look at what MEM is. MEM has words as one column, group as another column, right, in there. And so it indicates which score goes with which treatment in there. There's nice things that you can do if you have it in that format. Split actually splits out the word values there by group. So that command by itself will create a little list here where there's the SC values and the PL values and the no drug values. SApply applies some function to that list. So it does it list element 1, list element 2, list element 3, and reports it all to you. So I'm going to the summary command gives you a little more information. Right? So here's a subject bit. So it takes the group 1, SC, and this is a summary of the SC values. This is a summary of the PL values. This is the summary, and so there's the mean and median and things in there. You could put mean, you could put SD in there if you just want the standard deviation. You could put length. You could put about anything in there. Another neat kind of useful thing you can do with this is get a box plot. possible. So here's a box plot, side-by-side box plot of these three groups, right? Looking at this, do we need to do much testing to see that there's much of a difference here? Right? So this is no drug, placebo, and SC. Now it kind of looks like placebo has a little impact, right? People are forgetting more words or not remembering. Maybe, maybe there's something there, right? So, but anyway, it looks like at least one is that. So we would expect to not reject. We would expect to reject the hypothesis that they're equal. Analysis variance can be achieved a couple ways in R. One is through this linear models. This is a letter L and M, linear models. It's used in regression and for prediction. We'll use it again when we do linear regression and prediction. But it says that the outcome of words is a function of group. And since group is a factor, it's going to have the three different levels right there. And it tells us the data set. The data set is memory. These are the name of the variables there. And so the linear model gives you some output, and analysis of variance processes that a little bit further to give you the NOVA summary that we like, that we're looking for. So it gives us this analysis of variance table. The group, and it calls it group here. I called it group, right? So it used group there. If I had called this treatment instead, it would put treatment there. So, but it's the group. 2 degrees of freedom because there's 3 of those. Here's our sum of squares for group or treatment. They call it residuals instead of error. But that second line in there is going to be that. Mean squares, our F value, and it gives the p-value. This is what the probability that it's greater than that F statistic is the p-value, and it's 0 to many decimal places. And it has this little coding thing that if the p-value is between 0 and 0.001, it sticks 3 stars on the end. So it tells you it's highly statistically significant by putting those stars there. If you were running this on 50 variables and you need to look through a lot of output to try to find the ones that are the most significant, then that's kind of helpful. Right. So that's the basic analysis there, right? Along with this graph and the means, maybe the standard deviations in the groups to kind of summarize the data, sample sizes, and then this analysis variance chart, you get the significance, right? So it's highly statistically significant. There is some differences there. This quantiles from the F tells you what the cutoff for an F statistic would be. Right? So that's the upper 95th percentile for that F. Right? Degrees of freedom come here from this. And so it has to be bigger than 3.38 to be significant at the 5% level. But we're way beyond that. Right? The p-value over here, well, PF gives you the probability you're below that value, and you give it the 2 degrees of freedom. So 1 minus the probability you're above, right? The opposite of that. So that's the p-value that is there. Almost 0.2. Okay, yeah, that's the same number. So 0.00445655, right? So very small at the chance of having anything like that, if in fact these groups were the same. What would happen though in these were our SC data. What if these were, instead of this, what if people tended to remember 3 more words? What's going to happen to our ANOVA if in fact those scores were a little higher? So I can change them. And then I just copied the same command. I'm putting the new modified, the artificially modified ones in there. So now min2 includes these other ones. If I have these other ones, right, then my box plots are going to look like this. If that group, they remembered and were kind of more on par with the other groups, it would look like that. Right? This is a picture where there does not appear to be much difference. There still might be a difference, right? These two might be different from no drug, and placebo, scopolamine and the placebo might have kind of a similar effect, right? You're taking something as part of a memory study that's supposed to, maybe make you go to sleep. It tastes funny. Psychologically, it could affect how maybe you don't try as hard to remember if you know that you're not supposed to, right? So And if it tastes like this drug, then your mind might react. So if those were the data, and it was like this, right? And we ran this, there's a couple changes that happen, right? It's still, degrees of freedom are still the same. Right? Sum of squares, 11.012, is that the, right? The error sum of squares is still the same, 49,417, 49,417, right? So adding 3 to everybody in that group hasn't changed any spread, right? So in the sum of squares error, you take the values minus its group average. So if everybody shifted, that doesn't change anything, right? This one stays the same. But the 11 is a lot smaller, right? The sum of squares treatment. The difference between the mean, these are the medians on those dark lines, but the means aren't too far different, right? The sum of squares treatment goes down a lot. So then the mean square treatment goes down. Mean square error is the same, because it's the same sum of squares, same degrees of freedom. The F value is now only 2.78. It's not beyond that 3 cutoff value. So if those were the data, we wouldn't reject. Maybe if you had, hundreds of subjects in each of these 2 groups, maybe with a placebo effect and the effect of this drug would maybe that would be significant. But you might need a couple hundred more subjects to have a significant result with that type of difference. And it just gets a little dot here, right? So between 0.05 and 0.1, right? So it's kind of on the verge of significance. At that 0.05, it's kind of suggestive. So if this really was a little pilot study, right, of 28 people, and you got a result that said, oh, p-value 0.08, maybe there would be some rationale for continuing some type of study because you've done such a small number. It's kind of suggestive that there's significance. Maybe you'd use this to do a power calculation to determine how many subjects you would need for a really significant study, if you're interested in that. So then the question becomes, right, what would happen? What do you do once you have, in the case of the significant result, right, what happens then? So this one goes back over here. So if we had the original data and they were significant, there is some difference, right? Now we could want to do a confidence interval for each pair of means, right? And in the confidence intervals for means, how do you do a specific confidence interval for 1 versus 2, 1 versus 3, 2 versus 3? In this case, there's really the no drug versus scopolamine, and then the placebo versus that drug. You might be interested in comparing those two. Some people might not specify that they're really interested in looking at placebo versus no drug. Maybe that's not really of interest. So they might have 2 comparisons, although there could be 3 pairs. All right, we need an estimate of the common standard deviation. Sometimes this would be called the pooled one. In the 2-sample t-test, it's called the pooled one. But the mean square error is provides an estimate. The expected value of the mean square error is sigma squared, and so it's used there. Our mean square error is 1.977, so the square root is about 1.4. So a confidence interval comparing the second group to the first one. A difference of the means. There's N1 in the first group, N2 in the second group. So we have sigma hat times that thing for sample size. And the t-distribution we get to use here, this is, in our book, it's N minus I, so there's 28 subjects, minus the 3 groups, we could use this 5. If we only had 12 in one group and 8 in the other, we'd have 20. And we'd only subtract 2, we only get 18 degrees of freedom. If we get bigger degrees of freedom, then our t-values are not so big. Right? So we get to play with a little bit more precision. Right? We get to use a smaller t-value instead of something that would be a little bit bigger. Because we have 3 groups that are all estimating the same value of sigma. right? Bigger sample size for that one unknown makes things more precise. And so we get an average here that goes from about 1.89 up to 4.53 versus scopolamine, the placebo group is estimating on average about two words, 1.89 to 4.53 words on average more. That's seems like a pretty big effect on memory. Versus the other group, the placebo. The difference of those averages, we get to use the same thing here in one, and this one really should be in 3, right? That should be in 3 there. They're both were 8, so I don't think it affects the calculations per se. But 3.14 up to 5.78. So if you had pre-specified that you wanted to do those two things, you might do both of the tests, confidence interval at that level, 95% level. But some circumstances, we're doing a little bit more exploring. So we have 5 groups or something like that, and we're looking at all pairs. Well, there's a lot of pairs that you're looking at, right? And the chance that you'll find at least one of those to be significant, with all that testing, you have a better chance of finding something significant. So analysis of variance, this comes into an issue called multiple testing. So without so much of an a priori hypothesis, right, such as in this case, maybe the active drug, the scopolamine, would have the lowest scores, right? Testing is a little more exploratory. And so instead of testing all hypotheses at a fixed alpha significance level like 0.05, people tend to use smaller significance levels for testing so that the overall probability of making an error remains about 0.05. So like a family or global significance level, right? And so for instance, if you had 3 tests and wanted to test all 3 pairs, and we wanted to do a 0.05 level test, or then confidence intervals at 95%. Overall, right, and you're going to take half of that, the idea is if you have these 3 tests, a conservative procedure called a Bonferroni method. So Bonferroni method of multiple testing. Takes this alpha value, divides it by the number of tests. So instead of doing each significance level at 95%, this would be 98.3. Make them all a little bit wider to account for the fact that you're doing multiple tests. Okay. So instead of using a t-value of 2.06, it says for each one to use a t-value of about 2.56. Make each one, that'd be about 1/4 wider. So that adjustment means that if you do see a significant result, if it doesn't include 0 as a difference, then don't think that you're fooling yourself just because you've run a whole bunch of tests and happen to find a few out of your many that are like that. So it's basically the same formula. The difference in means plus or minus a t-value, where we replace it with this bigger one because of multiple testing, and then the standard error. So in these 2 cases, in this example, you still get confidence intervals that are pretty far above 0, or there's not really a question that then using the scopolamine drug seems to have an impact on short-term memory. In R, there's a couple of ways that this gets done. And this is an area where people have invested a lot of thinking about how to go about it, and it seems to be still an area that's somewhat evolving. It evolves, right? And so one way of doing that, so our data in the R part is stored in here in this data set memory, right? So it had scores for number of words remembered, And then people are either taking the scopolamine drug, they're taking a placebo drug, or no drug. And the box plot, the words as a function of group for this data set that we're looking at. The scopolamine drug that is a sedative seems to be associated with a significant reduction in words that are remembered in a little test there. And we did the ANOVA LM, and get this ANOVA table, which has a big F value and a very small P value, which in testing means there's some difference between the groups in terms of average. It's kind of the short update, right? And then we want to test is, if you just tested this one versus this, scopolamine versus placebo versus that, you might not really need to do this multiple tests. You might be able to get around. We're going to test two primary hypotheses. We're going to do it both at the 0.05 level. They're pre-specified, no adjustment. We're going to use just 95% all the time. That is done, and that's believable, particularly if you're doing like a kind of confirmation study that you have clear hypotheses. But if you weren't really sure and just testing, if this was instead of placebo but really a second drug, and you're just seeing is there any difference at all, it might be less convincing that way. There is something called pairwise tests, where you give it the quantitative values, your group values, and there's a p-value adjustment method called Bonferroni. This thing will give simply p-values, not hard to see at all with this size, for comparing groups. So if you compare placebo versus scopolamine, then the adjusted p-value is about, it's quite small. There's still a significant difference even after you adjust. Right? This next one is the no drug versus scopolamine, as the p-value is very, very small. It also gives you those no drug versus placebo, these two up here that were kind of overlapped more. The p-value for testing those, adjusting for the fact that you're doing 3 tests with this Bonferroni adjustment, is about 0.26. So those two would not look statistically significant. I don't think they're statistically significant even if you don't adjust. Because if you divide that by 3, you still get something more than 0.8, 0.08. It's still kind of large. In the literature, if you go into something, there's people publish papers where they have different ways of adjusting. Maybe you would take the most significant result and not adjust that one, and then adjust everyone after that. There's different strategies for doing this adjustment so that you don't have to do too strong of an adjustment. And the default is method by somebody named Holm. Benjamin Hochberg is a different one. These things are developing. It's a lot of statistical testing used to be really concerned with the situation where you had a few hypotheses about a few means and then a big sample size. A lot of the mathematics where as the sample size gets bigger, what happens to distributions. Well, with genetic testing and large data sets, things have kind of changed. Right? With genetics, you might have 40,000 or 100,000 genes you're testing. Now the number of means that you might be comparing to one another is enormous. Right? If we had a treatment and a control group or cases and controls for the disease study, and you're looking at where are these people different in terms of their genes, there's a huge number of tests that are done. And so new methods get developed for trying to say, well, what's the right calibration to still say something significant, even if you're doing thousands of tests. So anyway, these things give similar methods, but they change the p-value slightly. So if you're ever working in a study and people are reporting some method you've never heard of, it might be new or one of these different variants would catch on. To get intervals, John Tukey was at Princeton back in the 1950s, 60s, wrote a lot of articles about early computing, graphical statistics. So ideas like doing box plots or stem and leaf plots, a lot of that stuff originated with Tukey and his groups trying to figure out, well, what's better ways to look at data now that we have modern computers. Well, at that time it was punch cards, right? to run things through, and kind of a very clunky graphical display of things. How can you look at data in flexible ways? You know, discounting outliers, doing something besides just the average to really gain insight. So Tukey, and he had this this procedure called honest significant differences. It's a little, I don't know how to motivate it exactly, but it's looking at highest honest significant differences. Anyway, it's kind of the similar thing. So they speak of it as a family-wise probability of coverage. So you want 95% overall, 5% error total across many different things. And there's a way that gets done in probability models. What this one does for you, which is nice, is it gives you a confidence interval for each one. So the difference in averages is just a simple average differences. But it gives you a lower and upper confidence bounds that are there for each one, and a p-value is adjusted for each of those. So it's not too hard to get these adjusted things. The Bonferroni, if you start to get 5, 6, 7 groups, you know, and you're looking at the number of tests that you have, you get a pretty big adjustment, right? So, in multiple testing. So, if you have 5 treatments or groups, and you're looking at all pairs, I choose 2 pairs. So say you had 5. 5 choose 2, then it's 10. But if you had 10 different treatments, 10 different groups you're looking at, comparing 10 different regions or 10 different occupations or something. 10 choose 2 is 45. And so it grows pretty rapidly. And the idea about the Bonferroni procedure is you divide the alpha by the number of tests. And then you use a t-value that's like 1 minus alpha over 2 times, say, the number of tests. Let's just call it T, big T. And you use that percentile. Now for this testing, we're going to use n minus I as the freedom there. But that number increasingly, as you get out into a large number of tails, you're getting really out past the 99th percentile, and you're getting very large values. So beyond 3, 4, 5 tests, it's probably recommended to use one of those other adjustment methods. They're all trying to do the same, but I'm not going to make a big difference about talking about which one to do. The book describes one that you can use for the homework. If you put data into R, you can use the Tukey method to get confidence intervals and p-values. But there is this thing called studentized range. Again, Tukey would have multiple ideas on different things. So this is called Tukey studentized range distribution. And here on this table, A10 I'll refer you to the textbook for your interpolars. And this has to do with the distribution that you would have for random sampling, kind of discounting the idea that something has to be the most extreme. So it's kind of recomputing critical values, distribution values, adjusting for the fact that something has to be the biggest, so it's leaving one out. And so in this table here, you have this column over here, this new is degrees of freedom. It's going to be n minus I for our procedure over here. And then across over here, you have the number of comparisons. And so you would look, find your particular one here, the number of comparisons you're doing. And there's some value that's in here. And that value is used in the procedure described in the book. And so table A10 is in our book. It's not too helpful. It's appendix page A20, so you still got to find the appendix and look through the tables to find that. But when you're looking at the description of the procedure, you'll find that value in there. I don't know if that's used. Once you get your data into R, there's all these other procedures, so you wouldn't necessarily do this, but it's try to accomplish the same thing.
What page did you say that was on?
So I copied it here. It was one of these handouts. So this is this number that you need. Comes from A10, table A10. It's actually page A20 in the book. So some of the F tables have multiple pages. T tables have multiple pages and things. Yeah.
So M is the number of comparisons. Is that like the I that we just looked at?
So if you have so if I is say 4, and you're going to compare all pairs, right? Then you need to choose 2 of those. So 4 times 3 over 2 would be 6, and our value of n would be 6. So if you had 4 means and you're comparing all pairs to each versus each other, you're doing 6 comparisons, and it says use that value in there as a multiplier rather than your ordinary t. And it's doing the same thing as our von Peroni or the other things, where it makes things a little bit wider to account for the fact that there's a chance that even if nothing is significant, you'd find something being significant just by chance. But anyway, you'll explore that on a homework problem to get the idea of doing that for an illustration of this multiple testing problem. There are 2 things, one thing to mention. Okay, there are some assumptions that go along with analysis of variance. There is a model underlying this that says that the measurements in a group are centered at the mean, plus or minus some error. And the error is such that it's centered at this with some variance. So that the data from one group should look roughly normal around its average. And the next group should look roughly normal around its average. And they should have kind of the same variance. So you want similar standard deviations in the group. So if you look at the standard deviations and they're kind of within order of magnitude each other, it would be okay. If one is 10 times the size of the other one, then there might be an issue of one group being extremely spread out. We would want the data to be normally distributed. And you can look within each group. If they're normal overall, that's one thing, but they can also be normal within the group, right? And so you take each group and make a histogram or dot plot or things. You don't want any of those to be extremely skewed or with extremely big outliers. And the other thing is you do want independent observation. So if this wasn't independent observations, but you're looking at performance over time, or performance in groups working together, where one person's score depends on the other person's score, then it wouldn't quite match. So in this applied example of this one, we can look at the box plot. That's the second one. Just that group, right? Gives us some. It's, you know, the median's in the middle. There's not any enormous outliers sticking out there. But we could look at each group by itself. We could do a histogram of the words and for one of the groups, say among the Scopulpine. Now this is a pretty small sample size, so that doesn't work, so I'll get rid of the main thing up there. It's a real small sample size, so it's a little hard to say whether that's normal or not. You could look at the ones that have no drug also are pretty small. So it doesn't really work, or placebo, to say really one way or the other. You might also look at the normal quantile plots and see whether this kind of looks like a straight line. Now, these are integers, a number of words, and so it's a little hard to match it up to the assumptions exactly. But but there's not a situation where some of the scores are these single digits and then something else is over 100. There's not a massive outlier like that, and it's not all, you know, clumped at 0 and 10. So this, you know, would probably be worth noting that the data are small in size, they're integers. It's you know, there's not any really strong skewness, but it's not perfectly normal anyway. So what it could do is impact the p-values, the confidence limits to be a little bit different than ideal in terms of performance. But even in this case, it's not so sensitive. It still provides results that reject when there really are differences, and most of the time, and does not reject in cases where they're more close together. But we'll look at a larger data example on Wednesday in some other contexts, and then we'll be able to examine some assumptions a little bit more. What we will do on Wednesday primarily is something called two-way ANOVA. We're going to give a little introduction to it now. So instead of having just one treatment, say this was the drug that people have, treatment A, you can have a second treatment factor. So the drug maybe is, you know, the Scopulpine, the placebo, or the no drug, right? So for those three levels, and another treatment could be something like duration of study. Short versus long. Some people could study the words for a short period of time versus a long period of time. If you're studying something for a long period of time, does it enter your memory more and kind of survive having the drug effect or not? If it's just short, maybe it's accented. And so in our sum of squares table, we'll have a couple of things. We can have the treatment A effect for drugs. We can have a treatment B effect for drugs. And if we have multiple subjects on each combination of drugs with how long they study the word, some study Scopulpine, study for a long time, some get that drug and study for a short period of time, we can have an interaction between these things. it's very possible that, right, as I described, having a long-term study, there might not be much effect of that drug. It enters into your memory and you retain it better. But you might have most of the impact might be in terms of short-term memory, so it would have an interaction there. Then there also is error, because you have multiple people within each group, there's variability there. And then total. There's degrees of freedom associated with these. Sums of squares associated with these, mean squares, and then F statistics. And so just a very brief overview. So if you had I minus 1, I groups here, and J groups here, the interaction actually gets I minus 1 and J minus 1 degrees of freedom. And if you had n subjects overall, there are n times I minus J degrees of freedom here, so that's how it works out. We'll go through on where these things come from. But there's a sum of squares for the A effect, and a sum of squares for the B effect, and a sum of squares for the interaction. And there's this sum of squares error. They add up to a sum of squares total, but that won't enter into so much our testing. But it adds up, so we'll write it here. And mean squares are sum of squares divided by degrees of freedom. So just a mean square for A, a mean square for B, and a mean square for the interaction, and then a mean square error. And in this scenario, so one set of subjects, right? They're randomized to treatments on 2 different factors. We can test all of these things. We can test, is there a treatment effect? Is there a treatment A effect? Is there a treatment B effect? Is there an interaction between these things? And so we're going to test all of these different things in one big experiment. So our F statistic here is going to be the mean square error for the A over mean square error. Everything is relative to this mean square error. Where does it? We're going to have a B effect versus mean square error. We're going to have an interaction effect. And all 3 of those things are going to have F distributions. So we're going to get p-values for all of them. And the efficiency that's gained in this is that you get to study 2 or more factors, or 3 factors, 4 factors, 5 factors, at once in one experiment. Not have to redo the experiment for one thing, and learn a lot more for your efforts. It also can help make some of these effects bigger, appear to be bigger. Because by having these other things, part of the total sum of squares is taken away from the error and placed into these other categories. So A versus the error could be a bigger ratio by doing this. You can make your study of just A, your primary one, stronger, right, by doing that. So we'll work through that with an example, with a kind of an applied focus on Wednesday. Like I said, I'll post the exam solutions on Wednesday. So you'll be able to look at those. Good job, Melissa, in general, for that. Thank you.
This one I was actually Tammy.
Oh,
That's right when you were like, oh yeah, perhaps.
And she realized it was raining and she turned to my drum.
Yeah, Melissa does that too.
Yeah.
So
Yep,
funny.
you.
Like, I thought you had to go.
You and Day.
I can wait. Yeah. How'd you do my exam?
You don't have this kind of stuff.
What?
We'll do my job.
Yes.